Hello and welcome to Precalculus lesson number 11. In this lecture, we're going to learn about functions. A function is a special kind of relation which makes it necessary for us to understand what a relation is first. So a relation is any set of ordered pairs. So no restriction on what they need to be. So for example, here's a relation. It's pairing of, say, 1 and A, the number 2 and the letter B, 3 and C, 1D, etc. The object X in an ordered pair XY is called the first coordinate, or abscissa in the classic terminology, and the Y object is called the second coordinate, or ordinate in classic terminology. We hardly ever use the classic terminology anymore, but in case you ever ran into it, I didn't want it to seem strange to you. Now, a function f is a set of ordered pairs as well, just like a relation, but we have a restriction on it. The no two distinct ordered pairs should have the same first coordinate. Okay, so the relation that we had introduced initially in the first example also happens to be a function, because notice that no two distinct ordered pairs have the same first coordinate. So therefore, this relation also satisfies this restriction. So not only is it a relation, but it's a special kind of relation called a function. The set of all first coordinates, right? They're also called inputs, the 1, the 2, the 3, and the 4 here. That is allowed by the definition of a given function is called the domain of that function. And the set of all the second coordinates, so in this case the B, the C, the D, it's referred to, they're also referred to as outputs. That set is called the range of that function. So for this particular function we have here, notice that we can say that D, we usually use a script D for that, is going to be the set composed of 1, 2, 3, and 4, right? And the range, which we use script R for, is going to be composed of this the set containing the elements capital A, capital B, capital C, and capital D. And as you of course know, in an ordered pair, the order matters very much. As you know, in sets themselves, order doesn't matter. So, for example, the set containing the numbers 1, 2, 3, and 4 is the same as the set, written as containing 4, 2, 3, 1, for instance, right? The order in sets doesn't matter. The same as the set that defines a function itself. We could have put in the ordered pair 4D first, and then the 2B, and then the 3C, and then the 1A. Makes no difference. The order of the elements of a set doesn't matter. So in the case of a function, we're interested in the nature of the ordered pairs themselves. All right, so here we have a couple of other simple examples of functions with finite domains and ranges. So here, notice this function f is sending the letter A to the number 1, the letter B to the number 2, the letter C to the number 3. So we can write this function as the set of ordered pairs, right? A1, B2, C3. The domain would be the set of all the inputs. Notice that here it's a little bit different from the previous example. Here the inputs are the letters A, B, and C, and the range, which is the set of outputs, will contain 1, 2, and 3, right? Now, in functional notation, we can also say this. We can say f of A is equal to A, right? Is equal to 1, sorry. So read this as f of A is 1. Now, you do not say f times A here. Be very careful. This is a different use of this parentheses notation that we are applying here. So when you have a function and you just put the function and then parentheses and put an input inside there, you're talking about basically the output of the function a when the input is a. So what is the output of this function when the input is a? The output is 1, right? So that's why f of a is 1. What's the output when the input is b? 2. So that's why f of b is 2. Same goes with c and 3, right? So here I'm just indicating that f of a, this notation here does not mean f times a. This is functional notation. Here's another function g. G sends a to 1, b to 1 as well. Okay, so you may be thinking, well, wait, didn't you say no two distinct ordered pairs should have the same first coordinates? Yeah, we did. We didn't say no two distinct ordered pairs should have the same second coordinate. That's allowed. Okay, so it's no problem if two inputs have the same output. The problem is if one input has two outputs. In that case, it would be a relation but not a function. Okay, so here we can see g of a is 1, g of b is also 1, and g of c is 2, right? So here we have a perfectly good function. There is something a little special about this, isn't it? This kind of a function we're going to study later is called one-to-one, okay? This is a function, but it is not as special as this one because it is not one-to-one, but they still serve a purpose, okay? So here we're just reiterating the fact that as long as each input is associated with only one output, the definition of a function is not violated. Now, for a relation to be a function, it is not a problem for two or even more inputs to have the same outputs. Even if all the inputs, in other words, all the domain elements are mapped to one range element output, that's fine. You're going to find that they have a special name. Such functions are called constant functions. But even something that extreme is okay, as long as you don't have a single input even that has more than one output. All right, so as we mentioned, it is a problem for the same input to have more than one output because then the relationship would not be a function, or the relation rather. The following diagram depicts a relation between two sets that is not a function. Notice that here, the input A has more than one output. It's being mapped to both 1 and 2, so therefore this would not be a function. Now, if we put this relation H in the form of a set of ordered pairs, we would have the ordered pair A1, A2, B2, and C3, right? Now, notice that these two ordered pairs are different, yet they have the same first coordinate, and that violates the definition of the function that we have, a function that we have already discussed. Now, be really careful, because if they show you an example like this, you would not mark this as not a function, even though you can see you have the same first coordinate in two of the ordered pairs. But that's because they have the same second coordinate as well. In other words, this is a set in which an element has been repeated. Now remember, repetition is completely redundant when it comes to sets. And as far as set theory is concerned, this set containing these 4 elements is the same as this set, which now only has 3 elements without the repeated element, well, obviously being repeated. So therefore, this actually would represent a function. So be careful with that. While the functions described so far have finite domains and ranges, we may encounter many functions as we proceed in mathematics that have infinite domains and ranges. That just means domains and ranges containing infinitely many elements in them, right? Now, we've already seen a couple. We've seen linear functions of the form f of x equals mx plus b. with m and b being real numbers. And we've also seen quadratic functions of the form f of x equals ax squared plus bx plus c. Here, a, b, and c are real, and a shouldn't be 0. I mean, the only reason for that requirement is that then this term would collapse and you would end up with a linear function. So we just want to make sure that it is distinguished from linear functions by not allowing a to be 0. So here are two functions that, as we will see, have infinite domains and ranges. All right, next we're going to look at some commonly encountered functions along with domains and their domains and ranges below. Now, this function right here is basically the 45-degree line, right? It's a function f of x equals x. It is also known as the identity function, all right? So because basically for each point on the graph of this particular function, the x and y are identical. They're the same element, right? X equals y or y equals x, right? Now, so notice that there are no restricted values here. So the input can be any x value from the x-axis, and the output will be the exact same value, right, on the y-axis that would form the ordered pairs, right? So for example, you know that we have, for example, the ordered pair 5, 5 would be one of the ordered pairs if we were to write this as a set of ordered pairs to describe the functions, right? This particular function. So this is why the domain is basically the entire x-axis, or the set of real numbers, which can be written as negative infinity, comma infinity, right? And the range is going to be the exact same. So this got thrown over here. This is actually over here, right? So the range is also going to be negative infinity to infinity, right? Because you're going to get basically all the y values represented here as outputs, right? And so each ordered pair would have an input from the x-axis and an output, which would be representing the y-axis. This graph here for my point is not perfect. This should be a little bit further up, right? Now, here's another one, another commonly encountered function. This is the base quadratic function, f of x equals x squared. We call this the reference parabola because using this particular graph, once we learn about transformations of functions, we'll be able to graph other parabolas that are not necessarily sitting right here on the origin with their vertex, right? This lowest point of a parabola is called the vertex. We'll learn a whole lot about all that later. But notice that there is no restriction on what the inputs for this function are, right? Because you can have any x value and take it and square it, right? So it doesn't cause any kinds of errors. So all x values on the real number line here represented by the x-axis are going to be acceptable. Therefore, the domain is all real numbers, right? Now, the range, however, notice once you square any real number, the answer is, the output is going to be non-negative, right? The worst case scenario is squaring 0, which is going to give you 0. Otherwise, you square any number other than 0, you're going to end up with a positive number, right? So the range is not going to be all real numbers. The set of outputs, in other words, the y coordinates, or the y values that are going to be associated with the graph of this function are all going to be positive y values, right? Or non-negative, let's say, because 0 may be a value as well, right? So that's why we put 0 to infinity with a bracket on the 0, because we need to include 0 as one of the outputs of this particular function, right? How about this next one? This is called the cubic function, and Here, notice that no restriction on the inputs, right? Because you can cube any real number that you want without causing any errors. And notice the exact same would work for what? For the output, right? So the domain here is all numbers from negative infinity to infinity, in other words, all real numbers, and so is the range. So I don't know what happened to my table here, but this guy should be over here too. Okay, so the domain and range of this function are also all real numbers. All right, so here's another famous function here, the square root function. Now notice here, as you know, we want x to be non-negative, right? Because the square root of a negative number will result in a number that is not real, right? So therefore it would be imaginary. So as far as a real graph is concerned here, we want x to be greater than or equal to 0. That's why the domain here is the set of all numbers that are x values that are greater than or equal to 0. So if we were to write that in set builder notation, we would have all x such that x is greater than or equal to 0, right? Now, notice that the outputs are also going to be non-negative, right? Because when you take the square root of a non-negative number, you're going to get a non-negative value output, right? Now, notice how they look exactly the same, the domain and range, in interval notation. But if I put the range in set builder notation, I would say all y such that y is greater than or equal to 0. So the difference between them becomes obvious when you put them in set builder notations. Here we're dealing with all x values greater than or equal to 0. Here we're dealing, for the range, we're dealing with all the y values greater than or equal to 0. All right, here's the absolute value function, right? Notice that the domain here is all real numbers because there is no real number that you can't take the absolute value of, right? So any input is fine. And for the outputs, notice again, all outputs of an absolute value operation are going to be what? In this case, an absolute value of x, right? Are going to end up giving you non-negative results, right? So the range, once again, is going to be all x values greater than or equal to 0, which in interval notation just becomes bracket 0 comma infinity, right? And then parentheses. You never put a bracket, of course, next to an infinity or a negative infinity because those can never be included as numbers. They're numerical concepts, right? Okay, here we have the exponential function, right? This refers to situations where a quantity gets larger and larger in value very quickly, right? So you may have heard of exponential growth, but the same can happen in the opposite direction with a quantity falling very quickly, and that would be exponential decay. All right, so notice that the input can be any real number. So here we have for the domain all real numbers. The range, once again, for these is going to be the set of all positive numbers. Notice that here we don't even get 0 as a possible output because this curve right here is getting closer and closer to the x-axis asymptotically. Now it's hard to see that with a graph like this because it looks like it's touching it, right? But if you have a much more zoomed in graph, you would see that it never actually touches. Let's go ahead and take a look at it on a graphing application. Here we'll take a look at it in the wonderful program or website called Desmos. So here we have y equals e to the power of x. All right, again, notice at this kind of zooming, it's going to look like it's hitting it, right? It's crossing it, but it's not. As you start to zoom in, see, then you can see the difference that there is between the blue line and the x-axis. Now, the fact of the matter is the blue line will get closer and closer and closer to the x-axis, but it will never actually cross it. Now, this kind of an approach where one curve becomes gets arbitrarily close to another one. In fact, what do we mean by that when we say arbitrarily close? We mean you give us what positive value you want to get it within that distance of, and we can do so. Okay, so this curve is going to become closer and closer to the x-axis, but never actually touch it. So this is called an asymptotic approach, right? So therefore, here the x-axis plays the role of what's called a horizontal asymptote for this graph of f of x equals e to the x, because it's going to get closer and closer to it, but never cross it. All right. So here, notice the subtle difference between the ranges, right? Here we have bracket 0 comma infinity. Here we have parentheses 0 comma infinity, because we cannot include 0 in the set of outputs of this function. Okay, now e is a natural constant, kind of like pi, right? So the value doesn't change. It's approximately 2.7. Okay. All right, when it comes to testing whether you have a function or not, graphically, there's a really nice tool available to us, because it's very easy to verify, and it's called the vertical line test. Now, if no vertical line intersects the graph of a relation at more than one point, then the relation is also a function. Now, you can see in this simple example why a vertical line test would fail for relations that are not functions, because notice, for example, with the relationship, the relation that's described here is x equals y squared. Now, if you use both the values 2 and negative 2 for y, you would end up with ordered pairs 4, 2, and 4, negative 2. Notice the same first coordinate, but different second coordinate. So two distinct ordered pairs with the same first coordinate. So one input, two outputs. So this would fail the vertical line test, and you can see that this is not the graph of a function. Of course, it is the graph of a relation, just not that of a function. All right, for this example, we're going to state the domain and range of this relation, and also decide whether it is a function or not. So what I really like to do is to put all the first elements, or the first coordinates that are different, and line them up. We're going to make an arrow diagram. So we have 3, 4. I'm not going to repeat the 4. And then I'm going to put 6. Now I'm going to put the unique output elements, right? So negative 1, 2, 5, and 8. Now I'm going to make arrows indicating the pairings, right? 3 is paired with negative 1, so I'm going to put an arrow like that, right? 4 is paired with 2. 4 is also paired with 5, and 6 is paired with 8, right? Now, as far as writing the domain and range, that's simple. The domain is going to be the set of all the inputs, and of course, we do not repeat. We don't write the 4 twice, right? So we have 3, 4, and 6, all right? For the range, we have negative 1, 2, 5, 8, right? And notice that the same input here has 2 different outputs. So therefore, this is not a function. All right. The notion of a function is actually very simple, but extremely important. So please make sure you understand the nuances. All right, take a minute, see if you can do this on your own. You're going to state the domain and range of the relation, and then decide whether it's a function or not. Okay, so I think you can see the domain and range are quite simple, right? The domain contains the elements 4, 6, 7, -3. Notice order doesn't matter at all. You don't have to put the smallest number first or put them in any kind of an order. The range is the set containing 100, 200 and 300. Again, the order doesn't matter, but here they happen to be in ascending order. And we can see that each input here has only one output. So there is no problem, there's no violation of the function rule here, so this would be a function. Now, if you were to put it as a set of ordered pairs, right, this function would look like this, right? 400 is one of the ordered pairs. The next ordered pair is 6 and 200. And then you have 7 is also going to 200 paired with 200, and then you have -3 paired with 300. Again, no violation, so this is a function. Sometimes a relationship is given to you in the form of a table, right? Here, the x coordinates are given to you in the left column and the y coordinates in the right column. You will recognize this if you've ever done a graph of a function, right? So for the domain, of course, we have all the inputs or x elements. So the domain would be the set containing -5, 0, and 5. And the range, notice, a single element. We do not repeat, right, in sets. So we don't need to write 3 2s. We just write 1 2, right? So is this a function? Well, if you take a quick look at the arrow diagram, here we have -5, 0, and 5 for the domain elements, and we have 2 for the range elements, and each of these is going to the same output. But there's no problem with that. Remember, you can have all the inputs go to the same output, and that's not a violation. So this is called a constant function because it always has the same output, right? Namely what? 2. So this is a function. All right. Notice that as a set of ordered pairs, this function would be the ordered pair -5 2, the ordered pair 0 2, and the ordered pair 5 2, right? Those would be the ordered pairs in the set describing this function. Let's call it f. Notice that no two distinct ordered pairs have the same first coordinate. Yeah, all of them have this, are different, and they have the same second coordinate, but that's not a problem. We never said that can't happen in the definition of a function. All right, take a minute to pause the video, and you should do that for each problem, whether I remember to say it or not, and see if you can come up with the domain and range of this relation, and if to decide if it is a function or not. Okay, so one easy way to handle this is go ahead and write these in a arrow diagram, these ordered pairs. So let's go ahead and put all the unique inputs. So -1, 0, 1, 4, and 5, right? Now the unique outputs, we have 1, -1, 2, we don't need to repeat the 2, and -3, right? All right, so we have, again, let's double check, 1, -1, 2, and -3. So our arrows are going to look like this. -1 is going to be sent to 1, right? That's what this function does. 0 is going to be sent to -1. 1 is going to be sent to 2. 4 is sent to -3. 5 is also sent to 2. All right. So we can easily, with this arrow diagram, we can now easily write our domain and range. Domain is the set of all the inputs, so -1, 0, 1, 4, 5, right? Make sure you separate them by commas, of course. And the range includes 1, -1, 2, and -3. All right. Now deciding whether it's a function or not, remember, is any input being sent to more than one output? No. And notice that each output is associated with one input, right? One or more inputs. So therefore, yes, this is perfectly a fine function, right? No problem at all. All right, so there's a different kind of graphic representation of a function for you. All right, so as far as domain and range, notice that the ordered pairs that create this familiar oval shape, which as you know is called an ellipse, all the inputs, all the x values that would go into ordered pairs that would create this graph, right? Notice a graph is nothing but just a bunch of ordered pairs, right? At different points, right? Each point represents an ordered pair, right? So for all of those ordered pairs, the x coordinate or the first coordinate is going to come from somewhere in this region, right? Between -4 and 4. So that's where your domain is. So notice that -4 and 4 themselves are x values that participate in this graph as well, right? That contribute to the graph. So we have -4, 4 and brackets on both ends because both endpoints are included. How about the outputs, the y values that go into creating the ordered pairs that comprise this graph? That would be all y values between -6 and 6, correct? So that's what our range is. All right, so how about as far as this being a function or not? What do you think? Yeah, it fails the vertical line test quite miserably, right? In fact, we can, even just looking at it, we can see 1, 2, 3 visible lines that cross it at more than one point, right? This first line here, the line x equals 2, crosses it at that point and that point, right? The y-axis itself crosses it at 6 and 0, 6 and 0, -6. And of course, this line here would cut it at that point and that point. So yes, this fails the vertical line test. So not a function. Of course, it is a relation. You know, we have very little to worry about as far as naming something a relation, but it is not a function because it's just a bunch of ordered pairs creating this graph. So it is a relation, but it is not a function. Now, the question is, are these domains, are they finite or infinite? That's what I would like you to think about, right? Remember, here, when we say, is this a finite domain, we mean, does it have finitely many elements in it or infinitely many elements in it? Which one do you think it is? Well, as you know, between -4 and 4, there are a whole lot of numbers. In fact, there are infinitely many numbers. And the same goes between -6 and 6, right? Because you can't just be thinking of the nice numbers, 1, 2, 3, 4. No. You have to think of all the possible numbers, rational ones, irrational ones, etc. And when it comes to those, there are infinitely many, right? So both of these are considered infinite domains. All right. As far as an interval is concerned, are those finite intervals or infinite intervals? They're finite intervals. Remember that. Because when it comes to intervals, whether when you call them finite or infinite, you're talking about what? The length, right? The lengths of the both of these are finite. In fact, the length of this one is 8. The length of that one is what? 12. So as intervals, they're finite intervals, but as sets containing how many a given number of points, these are both infinite sets, right? All right, because remember, an interval after all is a set, right? So there we go. Make sure you understand that, please. All right, here's actually a commonly encountered graph. We didn't have enough space to get every commonly encountered graph in that screen that we were looking at, but this is actually a famous function. This is the reciprocal function. This is the graph of f of x equals 1 over x, right? Notice that we cannot use 0 as an input for this function because 1 over 0 would become undefined, right? That's why, notice, there is no output that you can see associated with this graph at 0, and the input 0 is also excluded. So the 0 is excluded from both the set of inputs for this graph as well as the set of outputs, right? All the ordered pairs that make up this graph, right, can come from anywhere on the x-axis, and the outputs appear to be associated with all points on the y-axis except for what? For 0. So the domain and range for this function are going to look very similar, right? What is the domain? Think about it before you watch the rest of the video. All right, so the domain, I'm going to write it for you in several different formats to really drive it home, right? So one way to describe it is just to say the set of real numbers, but not the element 0. We don't really call that a subtraction because it's set notation, right? So this is we're talking about all the numbers that are in set R, but not in set the set containing 0. Okay, so that's one way of writing it. Another way is to use intervals, right? Actually, since we use this set notation, let's go ahead and stay with that, and let's go ahead and discuss it as in set builder notation. So this would be all x, right, belonging to R, such that x does not equal to 0. Would you agree? Notice that sometimes books, they leave out the belonging to R part, but if you really want to be precise, you should really put that in. Now here, finally, we'll put it in interval notation. So it would be all real numbers up to 0. So that would be parentheses, negative infinity, comma 0, together with all real numbers after 0. So we're just excluding a single number, 0. So that would be 0 to infinity, right? All right, so what about the range? Well, the range is pretty much identical, except these are y values we're dealing with, right? When we write the range. So you can still write R not 0, right? And the only place you're going to see a difference between the domain and range as far as visually is when you write it in set builder notation, because here you're going to say all y belonging to R such that y does not equal to 0, right? Now again, when you go to interval notation, you're going to have all number y values from negative infinity to 0 union all real, all y values that are real numbers from 0 to infinity. So again, in interval notation, they're going to look identical. But you very well know that there is a difference between them in that here we're talking about x values, here we're talking about y values, right? They're coming from different axes. All right, so there is another function that we discussed. And this is, again, this is called the reciprocal function for obvious reasons. All right, so go ahead and pause and try this one. All right, so I think you can see that as far as x values are concerned, all of them are in play here, right? Notice this graph keeps going. It goes on in this direction forever, and it does go on in this direction forever as well, right? So eventually, each x value is going to be an x coordinate of some ordered pair on this line, right? I mean, on this graph, right? This is a parabola, right? It's a one that's facing downward, right? The opening downward. And also notice that all these positive x values here are also eventually going to be x coordinates of some point on this line, right? So so all x values are in play to create this graph. So therefore the domain is all real numbers, right? So we can write the domain is R, or we can say just negative infinity to infinity. If you want to put it in set builder notation, you can just say all x is that x belongs to R. That's it. All right. Now, how about the range? Are all y values in play when it comes to creating this graph, right? If you think about it, the answer would be no. In fact, there is no y value that would be a y coordinate of some point on this graph, right? That is greater than what? -4. -4 is the largest y value that contributes to this graph, right? As being the y coordinate of a point on this graph. So therefore, the range is going to be what? Is going to be all real numbers from negative infinity, but you have to stop at what? At -4. You include -4 because it is in play when it comes to graphing this vertex, right? So, all right, so how would you say it in set builder notation? Well, you would say all y such that y is what? Less than or equal to -4. That's how you would say that. All right, so what about whether it's a function or not? Does it pass the vertical line test, right? And I think you can see clearly, yes, it does. And there's no vertical line that crosses this graph more than once, right? So this does represent a function. All right, we need to go back to our friend here because I did mention that it is a function. It's called the reciprocal function, but we didn't decide why, right? So why is this the graph of a function? Does it pass the vertical line test, right? Well, if you look at it carefully and long enough, you'll see that indeed it does pass the vertical line test, right? So sometimes it looks like on this side, again, here the y-axis is going to be a vertical asymptote and the x-axis is going to be a horizontal asymptote for this graph. So this is going to become closer and closer to the y-axis, and at some point it'll look like it's really running parallel, right? Very, very close to parallel, but it never is. There's always going to be the slightest bit of an angle so that it is not really going to be a vertical line, so that because if that were, that would be a problem, right? Because then there would be some vertical line that would cross it, what, not just once but infinitely many times. So but that's not a problem because this is never going to become a straight vertical kind of a curve here. So therefore, yes, all vertical lines cross it once, at most once, and therefore, yes, it is a function. How about this vertical line? Well, that vertical line doesn't cross it at all, right? So our problem is not crossing a graph at all. Our problem is crossing a graph more than once, right? So this wouldn't cause any problem. All right, so I just realized we didn't do our vertical line test on this. That's why I wanted to take a minute to come back to it. All right, let's proceed. All right, how about this domain and range of this? Well, obviously, linear relation, right? We'll decide whether it's a function or not later. We do know it's a relation. Remember, every point on it is just some ordered pair, right? With the x value being the input, the y value being the output, etc., right? So when you look at this relation here, you can see all x values go into creating this graph, right? Because remember, again, this keeps going like this forever, and it keeps going in the other direction forever as well, right? So eventually all x values and all y values come into play when it comes to creating the points that are the ordered pairs represented on this graph, right? So the domain and range are both what? Are both all real numbers, also known as the interval negative infinity to infinity. All right, so does it pass the vertical line test? Yeah, notice that all oblique lines, right? And as well as all horizontal lines, right, do pass the what? The vertical line test. There's only one class of lines that miserably fails the vertical line test, and that's vertical lines themselves, because there is one vertical line, namely themselves, that would cross them how many times? Infinitely many times, right? So, but other than those, other than vertical lines, all oblique, which basically means neither horizontal nor vertical, so all oblique as well as all horizontal lines represent functions, right? Because they will pass the vertical line test. So yes, this clearly does pass the vertical line test. There's no vertical line that would cross this graph more than what? Once. So this is the graph of a function. All right. Now, here's a horizontal line. In fact, if you wanted to write the definition, it would be simple. I think you know that. Well, it's actually written as y equals 2, right? But if you replace y with functional notation, you can say f of x equals 2. No matter what the input is, the output is always what? 2. So this function sends all real numbers, right? Whether it's a half, pi, e, square root of 2, whatever, -5, you name it, right? It's sending all of them to one output, namely what? 2. This is exactly what we said is called a constant function, a function whose output is the same regardless of the what? The input, right? So yes, does it pass the vertical line test? Yes, it does. There's no vertical line that's going to cross this horizontal line more than once, right? So it is a function. What's the domain? Well, remember, every x value is in play here, isn't it, right? So the domain is all real numbers. But the range is far more limited. What are the, so let's look at some of the ordered pairs that create the graph of this function, right? How about 1, 2? How about -6, 2, right? How about -11, 2? How about 7, 2, right? Notice the y value or the output is always the same. What is it? 2. So the range contains a single element. It's not an interval. It's not any kind of a set that's larger than a single element 2, just like that. So this range contains a single element in it, all right, and that is 2. That's why we call it a constant function. All right, make sure you understand that, and we'll proceed. All right, here's a vertical line. In fact, if you wanted to write the equation, you would say x equals 2, right? Because remember, as long as you're on just living in the simple world of a number line, right? If I asked you to graph x equals 2, you just go to 2 and you put a dot there, right? And that's the graph of x equals 2. But if I ask you to graph x equals 2 in the Cartesian coordinate plane in two-dimensional space, I'm asking you to graph all points whose x coordinate is 2. So that would be all of the points on this vertical line, right? That's why the graph of this equation becomes an entire line in two-dimensional space, because for every point on this graph, right, on this line, this vertical line, what's the x coordinate? It's 2, right? Like, for example, this point here is 2, -10, right? This point here is 2, -5. This one here is 2, -2, right? That one right there on the x-axis is what? Is 2, 0, right? Like up here we have like what? This is like, for example, 2, 4, right? Then we have 2, 7 on the top there. Notice, for every point on this vertical line, the x coordinate is what? Is 2. That's why the entire line is the graph of the equation x equals 2. All right, so what x values are at play when it comes to constructing this graph, right? Well, not too many, right? Only one, namely x equals what? 2. So this relation has a very limited domain. The previous relation had a very limited what? Range, right? Remember this? That it only had one output, so the range was very limited. This is the exact opposite, right? Notice that here, the domain contains a single element, 2, and the range contains what? What is the set of y values at play when it comes to creating this graph, right? All of them, right? All y values are at play, right? So the set of y values associated with this graph, the outputs of this relation, are all real numbers. Basically -infinity to infinity, right? So this is what I was talking about when I said there is one kind of line whose equation does not represent a function, because the graph would fail the vertical line test miserably. So why? Because here's a graph and there is a vertical line, namely what? Itself, right? We never said exclude the graph itself. So including itself that crosses it, how many times does the vertical line x equals 2 cross the vertical line that's graphed? Well, it's the same line, right? So infinitely many times, right? So this is as far away from being a function as you can get, right? In fact, for this particular graph, if you were to do an arrow diagram, well, you wouldn't be really able to do an arrow diagram because there's too many arrows you would need. But just as a sampling of an arrow diagram, it would send every number. Like, let's say it would send 2 to 1, it would send 2 to 2, it would send 2 to 3, it would send 2 to whatever, a half. It sends 2 to square root of 2, etc. It's sending 2 to every possible element in the real set of real numbers. So therefore, So we just put a dot, 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 meaning, this doesn't end here, of course. So this is just a partial arrow diagram for this situation. So this would not be a function, obviously. Okay? And that's about it for this one. So all lines except what? Except vertical ones represent functions. That's the easiest way to say it. If you want to say it in a positive manner, you say all oblique lines and horizontal lines represent functions. All right, so here we want to state the domain and range of this relation given to us only with the use of an equation, and determine whether it's the relation is a function or not. Well, if you think about it, there is no restriction on what you can use for x values, right? And each one is going to give you a different y value, right? Each unique x value is going to give you a unique y value. So therefore, yeah, this definitely does represent a function. In fact, you can quickly graph it, right? We haven't maybe discussed it formally yet, but you've seen it in algebra. We know that here the slope is 1, right? mx plus b, and the y intercept is 4. So we start at the y-intercept, right? So 0, 1, 2, 3, 4. There is 1 point on this line, and you go up 1, right 1. So then you graph the line, right? So clearly this is the graph of a function because it passes the vertical line test. But even just reasoning it, we were able to see why this would definitely represent the function. All right, so, and obviously the domain and range, all reals for domain, all reals for range, right? So domain is negative infinity to infinity. The range is from negative infinity to infinity. And yes, it is a function. All right. So we could definitely handle this without graphing it because we know that when it comes to inputs, we don't want to create a negative radicand, right? Remember when you're looking at a radical problem, what's under the radical is called the radicand. Okay, so we know we want non-negative radicands, so that's what we're going to do. We're going to set 2x minus 1 to be greater than or equal to 0. Remember, that's only if the index here, this number that we put in here is called the index, the root, right? As long as that's even. Now, if it's odd, you won't have the same restrictions, right? So be very careful not to create such restrictions when the index is odd, only when it's even, right? So we want 2x minus 1 to be greater than or equal to 0. So 2x is greater than or equal to 1, or x is greater than or equal to 1/2, right? So for the domain, we're going to want all real numbers greater than or equal to 1/2, right? You can put it in set builder notation too, all x such that x is greater than or equal to 1/2. In interval notation, of course, it's bracket 1/2 comma infinity parentheses, right? Now, do notice that once we've taken care of that, then the outputs are going to end up being what? The outputs are going to end up being all non-negative numbers because the square root of each of these is going to give you pretty much every number from 0 and higher, right? So, so therefore, the range is going to be bracket 0 comma infinity, which is all y such that y is greater than or equal to 0. Whenever you have an inequality in your set builder notation, then it becomes redundant to say all y belonging to R. Why? Because it's only if you're dealing with real numbers that you can talk about inequality and comparing them, right? You don't compare non-real complex numbers when it comes to you know, being one being larger than the other, etc., because they exist in the plane, right? In the complex plane. And when it comes to comparison of numbers, we only do that for numbers on the number line. Okay. All right, so there is that. Let's go ahead and take a quick look at this in our graphing application just to verify what we've done. Okay, so we want y equals square root of 2x minus 1, okay? So notice that if this is 2, right, that's 1 and that's a half. Okay, so we had it right. Now if I just put a point right there, it'll show you the coordinates 0.50. So we if you notice, we had that. So notice we wanted for x values, we wanted x values greater than or equal to a half. So we definitely did that correctly. And for the outputs, notice all outputs are above what? The x-axis. That means y values well, on or above the x-axis, right? So y values greater than or equal to 0. So think of all points on this graph, right? You'll see. See? This is what's nice about an app like this. I could never demonstrate this by hand, right? So notice you get what? All these ordered pairs are ordered pairs that you get by plugging in different inputs. Like here, if you plug in the input 9.04, right? Or if you plug in the input 7.15, you get the output 3.647, etc. You can always try that if you're curious. But notice all the y values are what? Are greater than or equal to 0. There is no y value down here. I can't go further down because there's no graph there, right? So, and the set of all the ordered pairs, the set of all the x coordinates, right, is what creates your domain. That's why the x values have to be greater than or equal to 0.5, right? There is no point on this graph with an x coordinate less than 0.5. Notice that? And for the y values, they all have to be what? It's all y values or all real numbers greater than what? Or equal to 0, like that. All right, that's that. All right, so here we have another relation. We want to determine the domain and range and see if it's a relation or if a function or not. All right, now you're gonna find through experience that because of the fact that we kind of formally associate the letter X with the set of inputs and the letter Y with the set of outputs, right? So that's just an agreement we have in place, correct? So because of that, as you will see, this will end up not being a function. We took a quick peek at it later. Let's see if you remember it or not, right? If I just do a quick table here, right? Notice that 0 gives me 0. Here, because I have x given in terms of y, it's easier if I give y values first and then solve for x. So if I plug in -1 for y, I get -1 squared, which is 1 for what? For x, right? If I plug in 1 for y, I also get 1 for x. So notice the same x value 1 is being associated with two different y values, y and -1. So this is not going to be a function. As far as domain and range, right, notice that since the y is being squared, right, you're not going to get any x values that are going to be what? Notice all x values are going to be non-negative, right? So for x, domain being the set of all the x values is going to be what? 0 to infinity, right? Now, but I can plug in any y value I want, right? So the y values, the set of all the y values, are not going to be limited. So the range here is going to be negative infinity to infinity. Now, if I just use the 3 points that I have, I can get a quick sketch of this. So I have 0, 0, 1, negative 1, and 1, 1. So this is a sideway parabola, right? It's what we call a left-right parabola. Notice for x values, you want everything greater than or equal to 0. For y values, no such restriction. If you look at the ordered pairs, they can come from any place on the y-axis, right? If we take a look at a prettier version on Desmos, you'll see. All right, so here we want to graph y squared equals x, right? Now notice if I do that same trick that we were with, just running through values, right? Notice all y values are going to be represented here, right? Because this will keep going, right? And all negative y values, notice they're all going to be in play as well. And remember, these are all the ordered pairs that you get. We only look at a few when we're trying to make a table, right? But a computer doesn't have that restriction, right? Because a computer can do things very fast, right? So therefore, all these points are at play when it comes to graphing this relation. But notice x values start right here. There's no negative x value because there's no negative part of this. There's no part of this graph that extends into the negative x region, right? So there you go. And we know the algebraic reason for that because the y is being squared. So you're not going to get any negative x values out of this relation, okay? This relation can only generate what? Non-negative x values, right? All right, there you go. So clearly fails the vertical line test. In fact, here's a vertical line right there that crosses it more than once. It crosses it here and here, right? And we already actually showed it using just this example with 1 and negative 1. With the 1x value 1 going to both 1 and negative 1. So therefore showing that it's not a function. So this one is not a function. It is a relation, just not a function. All right, so how about this relation? If you look at it, kind of seems related to the reciprocal function, and it is. I mean, we will one day be able to graph this using the reciprocal function as our reference function. So we'll do some actions to the graph of the reciprocal functions to be able to obtain the graph of this function. Okay, so but notice this one is a little bit different in the sense that for the reciprocal function 1 over x, 0 was the problematic x value or input value because it made the denominator 0. Here, you don't want x minus 1 to be 0. So let's see what happens if it is 0. We get x equals 1, right? So 1 is a problematic x value for this relation because it would make the right side undefined because 1 minus 1 is 0. 5 over 0 would be undefined. So therefore, for the domain of this function, right, we're going to say it's basically all real numbers up to 1 together with all real numbers after 1. So what did we leave out? Yes, 1 itself, right? We left it out. So it's not part of the domain, right? All right. Okay, as far as the range is concerned, we should be able to obtain pretty much any y value we want, right? except for the one that would be associated with x equals 1, right? So for our range, we're going to have every possible value except, notice, no matter how small this denominator, I'm sorry, how large the denominator gets, right? Or how small if you go in the negative toward negative infinity for x values, this will get closer and closer to 0, but it never becomes 0, right? So therefore, we're going to have a range that's going to contain every element in it except what? 0. So negative infinity to 0 union 0 to infinity. That one we cannot get out of any, no matter what x value we plug in, there's no way we're going to get 0 as the output, right? We'll get some number very close to 0 if we want to by plugging in really large x values or really small x values, but not 0 itself. Let's take a quick look at the nice picture of this to see why this is happening. Okay, so we're going to graph y equals 5 over x minus 1. Okay, so let me make this a little bit larger at first. Okay, so notice that the one x value that is not going to be a possible input here was x equals 1. In fact, if I graph x equals 1, you'll see if I make that dashed, it would be a better choice because it's never actually, it's not part of the graph. The graph is never going to cross that line, okay? So x equals 1 here is a vertical asymptote for this graph. Now, notice it never also touches what? It never touches the x-axis. If the x values get really large, watch what happens. Look at the, I want you to look at the y values, right? What's happening? They're getting smaller and smaller and smaller and smaller, right? Notice? Now, if I keep going, let's say I go here. Now notice what's happening. They're becoming, what is 0.067? That's almost 0, right? Very small. But one thing you notice, it never does what? Never, the height or the y value never becomes 0, right? So that's why you cannot put 0 as a part of what? The set of your outputs, right? Even if x values become really small, a similar thing happens. See? Again, you're getting closer and closer to 0 now from the other side, from the negative side, right? Look. Watch. Look how close that is to 0. But it is not what? Not 0. Okay? So even though it looks like the line is touching, you know very well, because of algebraic reasoning, that it is not actually touching, right? So here, if you notice, x equals 1 is a vertical asymptote, and y equals 0, which is the equation of the x-axis, right? Y equals 0 is a horizontal asymptote for this graph. All right, so that is our understanding of this particular function. Now, if you go back to, you will see it does pass the vertical line test, right? Notice no vertical line is going to cross this graph more than once. So yes, indeed, it is a function. All right, so that's that. Make sure you understand it, and then we'll proceed. All right, so there are two main forms of the definition of a function. Note that all these definitions are basically equivalent, right? Well, here I say all because I kind of was planning on showing you even more than two forms, but I decided we stick to the two main ones, and then I forgot to change the all to 2. So, but the two main definitions for functions are, one, the one we have already seen, that a function is a relation in which for each distinct value of the first component of the ordered pair, they're exactly one value of the second component, or no two distinct ordered pairs, right, have the same first component, right, or first coordinate. You know how we said coordinate before? You can also say component. You can say entry. There are, different things. We also said you can call the first component the abscissa, or the second component the ordinate, etc. So the other very popular definition for a function, this is the one a lot of the people studying pure mathematics encounter. It used to be given in this form. We are moving more and more toward the set theoretic definition. A function f is a rule or correspondence or a mapping that assigns to each member of one set, called the domain, exactly one member of another set, called the range. The element y equals f of x, read f of x in the range to which an element x in the domain is mapped to, is called the image of x under f. So symbolically we write f maps d onto r. We can also say that, we can also talk about what it does to a given input, that it maps as input to an x to an output y for a specific element in the domain. The most common notation, however, is that f of x equals y, meaning the image of f under x under f is y. The image of x under f is y, right? So f of x is equal to y is read f of x equals y. This is referred to as functional notation. Never read it as f times x. I keep repeating that because of how important that is and how unfortunately some people continue to make mistakes about it. One other thing we need to clarify is what, you may have heard the words independent variable and dependent variable. If f is mapping x to y and y equals f of x, we call x the independent variable and we call y the dependent variable, because basically the value of y is going to depend on what f does to x, right? The action that f performs on x to give the output y. So that's why we call x the independent variable and y the dependent variable. Changing the value of x causes a change in the value of y, okay? And the value of y depends on the value of x. Now, some people will cleverly say, well, we can take an equation that's solved in terms of, that's given as y as some function of x and solve it for x and work it the other way around. Yes, that can be done, right? Not always successfully, of course, or in a clean fashion, I should say. We may have to split it into like two functions, but it's the general agreement that we have that we, as I said before, we use x as the input and the independent variable, and we use y as the output or the dependent variable. So we just, have agreed upon that. We could have maybe agreed in the beginning to do it the other way around, but we didn't. Okay, so we stick with what the general agreement among mathematicians all around the world happens to be. Sometimes it's useful to think of a function as a machine. So you have here this function machine, you feed it the element x, out comes the output, which is f of x, or the output y. Now, functional evaluation refers to when a function is defined as an expression in the independent variable x, and we find a specific image or value for different inputs by utilizing substitution. Let's take a look at what we're referring to here. Here we have this function that's defined in this manner, right? So f of x equals negative x squared plus 4x minus 3. We want to establish that f is a function graphically and then go ahead and find these particular outputs, right? So negative x squared plus 4x minus 3. Again, we're going to become very, very good at graphing this kind of quadratic, but until we completely accomplish that, let's take a look at the graph on Desmos. Negative x squared plus 4x minus 3. All right, so y equals negative x squared plus 4x minus 3. All right, so I think you'll agree that it does represent a function, right? No vertical line is going to cross this more than once. So we have established that it is a function. Now we want to go ahead and compute these particular outputs. We want to know what the output of this function is when the input is -1. So all we have to do to find f of -1 is wherever we see x in the definition of the function, we're going to substitute -1. So be careful that original negative is already there. It needs to carry. So we'll use parentheses whenever we want to do a substitution for a negative number. So plus 4 times quantity -1 minus 3. So now again, this negative carries. Now the square of -1 is 1. So we just get -1. The first negative is carrying. That's where that negative is coming from. This one is going to disappear because once you square -1, you just get 1. And then here we have positive 4 times -1, which is going to give us -4, and then minus 3, right? So we end up with what? They're all negative, so add and keep the negative sign, right? 8. So -8. That is f of -1. All right, so for f of 0, we do the same thing. We have -0 squared plus 4 times 0 minus 3. So that's 0 and that's 0. So we end up with what? -3. And that is f of 0. So now we want f of -u. Now, it doesn't matter what value u has. This is just a more abstract kind of computation, but if we do it the exact same way, so if I want f of -u, wherever I see x, I'm going to replace it with what? With -u. Just like that. So we get f of -u equals, now the square of -u, that's just going to be u squared, because the -1 squared is going to become 1 times u squared, which is u squared, so u squared. But the negative in the lead position here is going to carry. So we do end up with -u squared, positive 4 times -u, that's going to give me -4u, and then -3 just comes down. And that's it. There are no like terms we can combine, so we're done. Just like that. That's functional evaluation. All right, see if you can get this one and then come back, okay? All right, no matter how complex the input is, we do the exact same procedure. Wherever we see x in the definition of the function, we replace it with the desired input. So here we want f of 2b minus 5. So we go ahead and substitute 2b minus 5 wherever we see x in the definition of the function. There's only one x, and that's right after 3. So 3 times 2b minus 5. When you see 3x, of course, that means 3 times x. And then don't forget plus 4, right? So we end up with 6b minus 15 plus 4. So we end up with 6b minus 11. And that's going to be exactly what we're looking for, which is f of 2b minus 5. Okay, So that's just like that. Very simple, but very important. Okay, let's move on. All right, so here we have two different functions given using two different formats, and we want to find the output of 3 basically. We want to know what is the output of this function when the input is 3. So here we're given a set of ordered pairs. So the input 3 appears only in this ordered pair, right? And it's associated with what output? 1. Okay? So we can say f of 3 equals 1. Okay? How about this one? Well, if 3 is the output, the input, what's the output? When 3 is the input, the output is 5. So here, f of 3 equals 5, just like that. Okay, so for this function in this graph, we want to find f of 3, and then we want to also find the x value for which the output is 3. So these are two different matters, right? Remember, the f of x here is basically going to be the y value. All right, so if the input is 3, right, you basically just go straight up till you hit the graph, stop, and then go see what output that's associated with, right? And when you do that here for this line, we see that it ends up being what? 4. So in other words, 3, 4 is a point on this graph. Do you agree? So that means when the input of this function is 3, the output is what? 4. So f of 3 equals 4. But then they say find x such that the y value or the output is 3. So this time you do it backwards. You start at 3, right? You move horizontally till you hit the graph, then drop down to the x-axis. Well, that is if you're, of course, above. If you're below the x-axis, then you would move up to the... So just move toward the x-axis and stop, and you can see the input whose output would have been 3 would be what? Would be 2. So the x for which the x value, I'm being lazy here, the x value for which f of x equals 3 is x equals 2. Okay? That's that. All right, so be careful, make sure you understand what they're asking you. Here, they're giving you the x value and they want the outputs. Here, they're giving you the output and they want to know what input is associated with that output, right? So that's why you have to work your way backwards there. Okay, that's it. All right, sometimes the equations are given you in a way which is not solved for the f of x or y value. So what we're going to do is, in some instances, we're going to find the expression and take the expression and solve it, take the equation rather, solve it for y, and then express it as a function. Okay, so let's see what we mean by that. The procedure is very simple. We're going to solve the equation for y, and then we're going to replace y with f of x. So here's an equation. It's actually a linear one, as you can see. There's no higher power than 1. We're going to solve it for y and then write it as a function. So notice that you have negative 4y equals negative 3x plus 12. I'm just isolating the y term now. We're going to divide both sides by negative 4. So we get y equals, let's show it so we don't make any mistake. Remember, we're doing this. Actually, let me use a different color. So we're doing this. Now on the right side, it's going to get split up. So each of those is going to get divided by, negative 4, not 5. I mean, not. All right. Maybe I need a break. All right. not 3. So we're going to divide both sides by -4. So we're going to end up with y equals 3/4 x, and then this positive divided by negative will give us a what? -3. All right, so now all you got to do is replace the y with f of x to write it in functional notation. Remember, per our universal agreement, we have the y representing the functional value, or f of x. So that's why we solve for y, right? So we get f of x equals 3/4 x minus 3. Now we want to evaluate. So this is the first part of what we were supposed to do. Now we want to evaluate f of 1/2. So we're just going to replace x with 1/2. So 3/4 times 1/2 minus 3, right? So that's going to be 3/8 minus 3 over 1, right? So common denominator is 8. The first denominator is 8. No need to do anything to that one. But for the second one, we're going to go ahead and multiply the 1 on the bottom by 8. So we have to do the same on the top. So we get 3 minus 24 over 8, which is what? -21 over 8. All right, so that's f of 1/2, right? That's one of the things we wanted to find. And we also want f of a. For that, all we're going to do is replace x with what? With a. That's it. So 3/4 a minus 3. There you go. That's all you have to do. And we're done. So sometimes it's possible to do this when what? When it is possible to cleanly solve the original equation for y. All right, so notice, for example, if we were asked to do this problem for, say, y squared equals x, we wouldn't be able to do it as seamlessly, because if I just apply the square root property, I get y equals plus or minus square root of x. So I would actually end up with two functions. I would get y equals square root of x, or y equals negative square root of x. I wouldn't be able to just get one y value which is going to work. And remember, when it comes to this type of equation with simple powers of x and simple powers of y involved, whenever the y term has an even exponent, you're going to run into this kind of problem, right? So you're not going to be able to usually write those as what? As a function of x, right? You're not going to be able to simply and seamlessly solve those with y in terms of x. So not easy to write those as a function. You would have to decompose those into more than one function. So always remember that when you have the even exponent on the y term, again, when we're dealing with simple scenarios like this with usually no more than one y term and no more than one x term, then whenever the y has an even exponent, we're not usually going to be able to write it as a what? As a function in this manner. All right, so that's that. All right, so now we want to talk about this really important property of functions, which has to do with the behavior of the function. We want to know that if a function is well defined over a given interval I, right? What do we mean by saying that f is said to be increasing on this interval? What we mean is that whenever you look at two inputs with one input being less than the other, like here, for example, 3 is less than 4, right? As long as the output of the first input is less than the output of the second input, that means the function is doing what? Going up like that, right? So therefore, we say the function is increasing over that interval. Now, it's decreasing if the opposite happens. Like here, for example, notice -4 is less than -3, right? But notice that the f of -4 is going to be somewhere up here. F of negative 3 is somewhere down here. So it's the opposite relationship. X1 is less than x2, but f of x1 is greater than f of x2, right? So in this case, we say the function is decreasing. X values increase, but the corresponding y values do what? They decrease, right? The last scenario of interest is when the function values do not change over a given interval. For example, notice between negative 2 and 2, the function values remain the same, right? So we say in this region, it's constant. Whenever x1 and x2 belong to the interval, their functional values are going to be equal. That's when we say it's constant. So now notice that this particular function is decreasing for x values less than negative 2. It's constant for x values between negative 2 and 2 inclusive, right? Including negative 2 and 2. And it's increasing for x values greater than 2, right? So visually, it makes a lot of sense, right? Make sure that it doesn't just make sense to you visually. I do need you to become comfortable with mathematical language of this type so that you can really advance yourself mathematically. The way you know if you understand this kind of language is see if you can reproduce it on your own, not with memorization, of course, right? By just seeing if it makes sense, right? What should happen if x1 is less than x2 for a function to be decreasing? What should happen for it to be constant? What should happen for it to be increasing? So by reasoning, right? Memorization, pure rote memorization is going to do you absolutely no good in mathematics. All right, so it's only understanding that's going to make math both enjoyable and beneficial for you. All right, test your understanding, see if you can tell me where this function on what intervals or open intervals it is increasing, where it's decreasing, or where it's constant, right? See if you can come up with that. All right. How about for all the x values less than negative 2? What is it doing? Is it increasing, decreasing, or constant? Notice what's happening. As x values increase, what happens to the y values? They decrease, right? So therefore, this function, you always want to look from left to right, right, to make your determination. You don't want to come back and tell me, but look, if I go this way, the values are what? The y values are increasing. Well, we don't deal with these kinds of graphs in that manner. We always consider what happens as x values increase, right? So we always want to look from left to right. Now, as x values increase in this interval from negative infinity to negative 3, what is this function doing? The y values are falling, so therefore the function is decreasing. So this function is decreasing on this interval, negative infinity to negative 3. All right. Now, at negative 3 itself, at negative infinity to negative 2, not negative 3, sorry. Now, at negative 2 itself, remember, we're talking about the x values here, right? So that's why it's negative infinity to negative 2. Now, at negative 2 itself, it's neither increasing nor decreasing, okay? So you don't want to include negative 2 as part of either interval of increasing or decreasing, all right? What is happening between negative 2 and 1 when x is negative 2 on the interval from negative 2 to 1? Notice as the x values increase in that interval, the y values what? Also increase. So therefore, it's increasing on the interval from negative 2 open interval, remember, to 1. All right. So what is happening from 1 to infinity? For x values larger than 1, what is this function doing? It's just constant, right? It doesn't change, and the y value doesn't change at all, right? So we say it is constant on, normally we like to just give these for open intervals, but you could in fact include the 1 in the interval where it's constant as well. But let's go ahead and answer it using open intervals only, because that's what they're asking, right? So we can say on 1 to infinity. Okay, so this function is decreasing for x values less than negative 2. It's increasing for x values between negative 2 and 1, right? It's increasing. And for x values greater than negative 1, the functional values don't change. So it's a constant function after that. All right, so that's how you do that. All right, so the last one for the road is going to be a kind of a quick application. This graph shows the relationship between the height of a kite in feet, h of t. So in other words, the vertical axis is representing the height of a kite, whereas the horizontal axis is representing the time in minutes. Okay, t. Use the, now remember, you don't always have to use x and y for your letters here when it comes to the Cartesian coordinate plane. You can use letters that make more sense with the situation that you're dealing with. Now we're going to use the graph to respond to these questions. What is the maximum height the kite actually achieves, right? Notice that means the what? That means you're going to look for the highest point here, the point that's associated with the highest y value or h of t value, right? And if you notice from here to here, that's 100, so that must be the it's 50, so that means that must be the 25 unit mark. So 150 plus 25 will give us what? 175, right? And remember, the height is in feet. Now, when is the maximum height reached? Well, notice that happens right there. So if you just come down, you'll see it corresponds to what? T equals 5. So when is it reached? After 5 minutes, right? Or you can say right at the 5th minute. All right, after the kite reaches its maximum height, it begins to fall, right? Right there. The heights are decreasing. What's the minimum height as shown on the graph? Now be very careful, because here they're giving you the specific period they want you to look at. Otherwise, the minimum height is going to be what? On the ground, or 0, right? So so they say between 5 and 15 minutes. So from here to here, right? In this time period, what's the minimum height? It seems to be right there, right? Which corresponds to what? 125. Remember, each tick mark represents 25, right? So the minimum height between 5 minutes and 15 minutes is going to be 125 feet. It looks to happen right there at t equals what? 10. So we can just say at t equals 10 minutes. Now, when is the height of the kite increasing? Well, remember, the height of the kite is increasing once from here to here, right? So from t equals 0 till t equals 5, right? Then it falls, and then it starts increasing again, right? From where? From t equals 10 to t equals 15, right? So it's increasing on 0, 5, and 10 to 15, right? Now, where is it decreasing? Well, let me write this a little bit nicer. All right, so it's decreasing on 5 to 10, right? 5 to 10, and then 20 to 25, right? It's also falling here. So 20 to 25. So on the interval from 5 minutes to 10 minutes, and the interval from 20 minutes to 25 minutes, okay? So in that region, time period, it's also falling. And where is it constant? The height seems to be hovering at the same height on what interval? From here to here, right? So from 15 to 20 minutes. So on this interval between 15 minutes and 20 minutes. So describe the height changes indicated by the graph. Well, this kite starts obviously on the ground, right? And then it starts elevating to a maximum height of what? 175 feet. Then it starts to fall for a few minutes, right? Until it reaches a minimum height of 125 feet during the next 10 minutes or so. Then it starts to gain height again, or elevation, until it reaches around 150 feet and stays at that elevation for about 10 minutes, right? Or what is it? 5 minutes, right? From 15 to 20. And then it starts falling to the ground over the next 5 minutes. All right, so that's basically what the behavior of the height changes are for this kite. All right, so please make sure that you understand the problems in this video lecture before attempting homework, and that should take care of it for this lesson. You take care until the next one.